So yeah, can you see my screen?
Yes, we can.
Yeah,
Perfect.
great. So okay, today we are going to talk about Intel application debugger, and we will learn how to debug heterogeneous applications on Intel platforms. And we will cover two topics: OpenMP offload and DPC++ application, because both of them are targeted to GPUs. So yeah, let's look at system requirements first. So as you see, we support Windows 10 and Windows 11. Visual Studio is supported as 3 latest releases. So, but well, please note that Visual Studio 2017 is discontinued, so the support will be removed in future releases. So I would recommend you to migrate to the latest one. So graphics, Gen 9 and Iris graphics are supported as GPUs. FPGA is supported as emulation device only, and you see only this list of CPUs. It was Windows. So on Linux, you see that devices are the same. As IDE, you could use Eclipse and Visual Studio Code. And also, I listed here the latest list of Linux distributions supported, but I encourage you to check release notes and system requirements. I put links here in the bottom of the slide. So I encourage you checking these links for each release, because they are really, they change really often. And we are going to switch to the first demo. For those who planned to play with this demo offline after this presentation, I would recommend to start with Get Started Guide to configure the debugger. And please note that you need to install debug companion driver. We do not install it during oneAPI installation because it requires root privileges. So you need to install it after oneAPI. And also you can play with array transform sample. It is targeted to debuggers, so you can play with it to make sure that that everything is fine. And today's demo is the second sample which we prepared for the debugger. It's Jacobi sample. Oh, sorry, yeah, I forgot to mention that you always need to source Intel oneAPI variables if you are going to use the debugger, so and other Intel oneAPI tools. So don't forget to do that if you are going to do to play with these samples offline. So yeah, well, Jacobi sample is a DPC++ application that solves a linear system of equations. We are multiplying matrix A by vector X, and it equals B. And X is our solution vector. Vector B is set in the way that all components of the solution vector are 1. However, Jacobi-backed CPP returns you incorrect result for vector X, and you need to fix to find and fix bugs. So we've prepared a bugged version, so you can play with it, and we prepared a fixed, so you can check your solutions. This is a short. The next 2 slides are for those who are going to play offline, and I'm switching to the terminal. Yeah, okay. So yeah, there are 3 bugs. 2 of them are you need to fix on CPU, and the third one is on GPU. So I recommend you to follow the order of bugs. First, fix bug 1 and bug 2 on CPU, and then switch to GPU. And today we will fix only one bug. I have already prepared the environment, but you need to source. I just remind you again about it. And we are going to build a sample. I need Jacobi bugged CPP, so I have this file here, right? So I need Jacobi bugged CPP. Note that you need to build with options G and O0. Yeah, it's and O0. G adds debug information to the executable, and O0 is needed to disable optimizations. Actually, you can try debugging application built with O2 or with any other optimization level, but you will possibly see optimized out message when you try to evaluate variables. This happens because optimization changes everything in your code, so including line order, line numbers. We are working on adding such capability to the debugger, but it is, it's too early to promise you this feature. Okay, so let's build the example. Oh yeah, so yeah, it looks like I need to source. Yeah. Okay. And let's run it. We are going to select the target, a CPU as a target, just using a command line argument CPU. And yeah, you see that it fails with bug 1 and give us some hints. We need to find some components of XK that are not close to 1. To examine variables, we need to find where actually we are going to set a breakpoint. So let's open the source file and see where XK is computed. Jacobi bugged CPP. Okay, so you see that there are some standard includes, buffer struct, and okay. So this is our main computation function. We see qsubmit here. This is a DPC++ kernel and 3 accessors in it. This is a host code. So this is not a device code yet. And accessors is an abstraction which is working with buffers, and it is just a way how we can work with memory in DPC++, because you know that CPUs and GPUs have a separate, have their own memory, and we need to access host memory from device, and so we need some mechanisms for it. And buffers is an abstraction for memory, and accessors is an abstraction how we can use it from the device. So Parallel 4 is our kernel, and this is where actually device code started. And we see that XK is computed somewhere here. So I guess that, since buffers is an abstraction for arrays, then I guess that something is wrong with array bounds with these indices, because, we are working with I here and we are subtracting indices. So let's check this running under the debugger. And yeah, by the way, we need line 77 for it. Let's set a breakpoint and see what happens. So yeah, I'm running the debugger using command gdb oneAPI, args command line argument, and this is my executable with its arguments. Actually, you can run it just gdb oneAPI and your executable, and pass the argument to run command inside the debugger, but I would prefer this one. It's just easier to control all the command line arguments, especially when I have a list of arguments. So okay, what else we can see here? Yeah, you see reading symbols from Jacobi bugged. It means that debugging symbols detected and loaded just because we added G option. And we can start debugging. I'm going to set a breakpoint to line 77. This is just a standard GDB command, and run. Yeah, so we hit a breakpoint 1, and let's print I value. And this is our array index. Yeah, it's 26, and it's absolutely safe because we are subtracting just 2 from 26. Let's see the next thread and check it here. Yeah, it's 18, and it's safe as well. And you see that we are switching between threads inside the CPU kernel. So yeah, info threads command shows us how many threads actually we have. So yeah, at least 25, but you know, there are much more threads. It's 98 threads, and there are really too many threads, and each of them contain different compute different I values. So I would suggest you adding conditional breakpoint to test our hypothesis that index subtraction leads to the issue. So let's remove the first breakpoint and set up a conditional breakpoint. It is just pretty straightforward. So it's break 77 if I less than 1. Just because I subtract 2, so I'm trying to check whether I have some negative array indexes. Setting this breakpoint and running. Yeah, so run it from the very beginning, and yeah, this breakpoint hit. So it means that I really have some negative indexes. And this thread contains negative index. Yeah, let's quiet the debugger and see sources once again. So what we need to do here is to add some if condition, right? To check that we are not trying to reach negative indexes. So we need something like this. If I more than 1, then we will compute this index, and so on and so on. So this is I more than 0, and so on. I'm not going to stop here for a while, and just what I'm going to show you next is the GPU debugging. You will see how it differs sometimes. I suggest you continue playing with this sample offline, fix all bugs, and yeah, I'm moving to GPU. To switch to GPU, I need to run it to change my command line argument and run the debugger again. So we are going to stop at the same breakpoint because it is in kernel code. So now our kernel will be executed on GPU. So I'm setting the same breakpoint and running the application. Yeah, so you see that the application changed here. It is executed on Intel Iris Xe graphics. So this is real GPU. And let's see where we are. So info inferiors command shows us that we are on a device. And now let's list all, all the threads. You see how thread names differ. This is CPU threads, right? And this one are GPU. You see that we have one more index here. Actually, this is a CMD lane for each thread. So each thread contains 8 CMD lanes, as you see. And actually, you can switch between threads using command thread. Unit. Now we are in thread 2.1. For example, I'm going to switch to thread 2.2 and CMD lane 1. Yeah, you see that I'm here, right? Let's go and see local variables for this thread. I need command info locals, and this is 49. I equals 49, xk equals 8. Yeah, okay. Also, I'm going to show you an alternative how we can inspect I for all active CMD lanes at once for this thread. So it's I need thread apply thread apply 2.1 asterisk instead of CMD lane index and print I. Right? You see that I printed all the I values for each CMD lanes for thread 2.1. Also, I can print I for all CMD lanes. This is just quite intuitive, so you can use all lanes and print I with thread apply. Right? So this is all the CMD lanes. Also, you can check registers, and you need inforec command, right? You see all these GPU registers here. You can also inspect disassemble. And as you see, if I press next command or even continue command, you see that we are just switching between threads. And what if I'm going to step to the next line? So to prevent intervention of other threads, I recommend you using set scheduler locking off command. And now I can, well, okay. So, well, this is what actually I was going to show you for DPC++.
Alina,
Yeah,
please watch out your time.
yeah, sure, okay. How many time I have?
We have 3 minutes.
Yeah, great, that's enough. So this is for OpenMP offload. Please know that it is supported for Fortran only. Oh, sorry, for C++ only. It's not supported for Fortran yet, so we are working on it, but it's not yet supported. This is what you actually how you are building C++ application using OpenMP offload. Just the same, you need to build with O0 and G option. But to enable debugging, you need to also disable device code optimization using one of these environment variables. Also, don't forget to set up the offloading variable to mandatory, which means that you are going to offload always to the device. And after that, you are ready to run in the debugger. So I'm not going to switch to the terminal right now, but I think this is enough to give you the first impression, because in the debugger, it will look exactly the same as I've just showed you for DPC++. And yeah, there are other debug capabilities. I'm going to show you what you also can do without the debugger. If you are working with some SQL plugin interface issues, then you can use SQL PI trace to see where your DPC++ application fails. If you observe some issues with your GPU drivers, GPU backends, then we have two different tools for each of the available backends. So that tracer for level 0 and OpenCL intercept layer for OpenCL. Also, there is a great option for debugging oneAPI offload. You can play with libopenMP target debug variable, and you can ask the runtime about different level of debug information. So just using different values, starting 1, 2, or 3 as value for libopenMP target debug. And yeah, this is just what you can also learn. I suggest you checking basic documentation and code samples for the debugger, and also remind you to check release notes and system requirements for each release. And there is, for advanced users, there is a special paragraph in our oneAPI programming guide. And also for those who are interested to learn more about oneAPI offload to GPUs in general, not only about debugging, we have a special course on DevCloud. So just follow this link and you will see everything that you need. So thank you for your attention. If you have any questions, please feel free to send me an email and I will be happy to answer you. So that's all. I can let me stop sharing.
Thank you so much, Alina. This was very insightful. I hope that the people in the audience have gained a lot of knowledge from Alina's presentation, as well as from today, a little recap of what